Hello, today we are looking at differential equations. Today's going to be just an introduction to differential equations. After you finish this handout, you will need one piece of paper. I added a problem that I want us to do, and it's not included in this handout. So please make sure you pause the video right now if you don't have a piece of paper and go grab one. Now, differential equations we are going to touch on in calculus, and when you go to college, differential equations is actually going to be an entire course that you take in college if you do study a topic in math. So let's just talk about the difference between a differential equation and an algebraic equation. When you have an algebraic equation, you get an answer that is a number. So if we started with 3x plus 2 equals 14, we could solve that and get x is 4. The way I could check it is I can take the 4, plug it back in for x, and decide if that does make a true sentence. And that one does. With the next one, 6e to the x equals 12. First thing I would do is divide by 6 on both sides and get e to the x is equal to 2. Now to get the x out of the exponent, I would take the natural log of both sides. And when I do that, I get the natural log of e to the x is equal to the natural log of 2. And with this, I can use my log rules to simplify that by bringing the exponent down. And finally, I know the natural log of e is just 1, so x is natural log of 2. So again, that's two different ways to deal with an algebraic equation. One, I just showed you how to verify a solution, and the second one, I told you how to find the solution. Now, when we move on to differential equations, this is a differential equation, and this is a potential solution to that equation, which means if I were to plug y in here and find dy dx, take that and plug it in here, I should get a sentence that's true. Both sides are equal. The next one is one that we should recognize. If I start over here with the tangent inverse of x, I should know that the derivative of that goes here, which means if I'm doing an antiderivative, which is basically what I'm doing, if I did an antiderivative of 1 over 1 plus x squared, I should recognize that to be tangent inverse of x plus c. And again, we'll talk more about how to solve those. Most importantly, though, it's an equation that gives you information about a rate of change of an unknown functions. Mathematicians, of course, as you know, are lazy, so we call these diff EQs. Instead of actually saying differential equations. So let's look at example 1. All we're going to do is we're going to verify these solutions for the equation that we've been given. So the first one is algebraic. So let's start by looking at x is equal to 10. And what I want to know is that really a solution to the absolute value of x minus 3 equals 7? So to do that, I'm going to replace the x with 10. So the absolute value of 10, and then I still have minus 3 equals 7. Sorry, close my absolute value. And the absolute value of 10 minus 3 is 7. And so the absolute value of 7 is 7, and 7 is equal to 7. So I've just verified that x equals 10 is a solution. We'll do the same thing with x is equal to negative 4. So I start by replacing my x with negative 4. And then let's work it out and see if I get the same thing on both sides of the equation. So when I work that out, I get the absolute value of negative 7 is equal to 7, and that again gives me 7 is equal to 7. So I have just verified both of those equations are both of those answers are solutions to the equation absolute value of x minus 3 is equal to 7. So in the next one, we are going to verify that we have y equals 3e to the 1.5x and y equals negative 0.5e to the 1.5x. So what we're going to do is we're going to verify that they are solutions to this first order differential equation. Here's my differential equation, or rate of change. So what I'm going to do is I'm going to start by taking the first one. We think that this is a solution. So what I need to do with that is I need to find dy dx. And if I find dy dx of that, I get 1.5 times 3e to the 1.5 x. So the derivative of e to the 1.5x is e to the 1.5x, but I need to multiply by the derivative of the inside, which is where the 1.5 comes from, and the constant 3 is still there. But that's not what I have circled in blue. So what I have circled in blue is I have dy dx, I've got that, equals 1.5, I've got that. And then it says times y. Well, what is y? Let's see, y is right here. Y is this thing. And isn't that the same as this thing right here? This is actually y. So I can replace that with y, verifying that y equals 3e to the 1.5x is indeed a solution to the differential equation dy dx equals 1.5y. So let's try the same thing with our other equation. We have this other y right here. So I'm going to start by finding dy dx, and that's going to be 1.5 again, times my constant, negative 0.5 e to the 1.5x. And let's compare that with what I have in blue. In blue, I start with a dy dx. I have that. 1.5, I have that. And then I have this thing, negative 0.5 e to the 1.5x, which is also known as y. So I can substitute that in. And again, that gives me the same dy dx that I had. Dy dx is 1.5y. So all I've done is verified that these equations are solutions to a differential equation. That's all I've done so far. Now in example 3, I'm doing the same thing, except now I have a second order differential equation, and it involves the second derivative. Okay, well, I'm going to do the same thing. So let's start with my equation that I think is a solution, and I need to find dy dx. And when I find dy dx, that is derivative of the inside is 2. The derivative of sine is cosine of the same thing. So this is my dy dx. But I don't want dy dx, I actually want the second derivative. So let's do it again. So the second derivative is going to be the derivative of what I just found. So my constant will stay. The derivative of the derivative of the inside is 2. The derivative of cosine is negative sine of 2t. So I have this, which, let's simplify that, is negative 4 of sine 2t. Now what I need is I need to do some substituting into the equation I have boxed in blue and see if I get an equation that is true. So the second derivative, so that's this thing, that is what I have in green. So I have negative 4 sine 2t, and then I've got plus 4 times y. Y is what I've circled in red. So that's sine of 2t. And the question is that equal to 0? So when you take a look at that, I have a positive 4 sine 2t, I have a negative 4 sine 2t, so 0 is equal to 0. And yes, that verifies that y equals sine of 2t is a solution to my differential equation, the second derivative plus 4y is equal to 0. So the last thing, we talked about two different differential equations. We have a first order differential equation, and that was from example 2. And the example 3 has a second order differential equation. And I hope that that's obvious at this point, that the first order differential equation has to do with the first derivative. And the second order differential equation has to do with the second derivative. Okay, on to the back. Onto the back, all we're doing is translating. So this is not calculus. This is Algebra 1 and Algebra 2. So what we need to talk about are direct, inverse, and joint variation. So a direct variation is something where we multiply k times our variable, and it's multiplication. Our inverse variation is where we have k divided by our variable. And joint variation is again a product of two different kinds of variation. Again, k is our constant of proportionality. So we're going to do number 1 together, then I'm going to ask you to do the rest on your own. So number 1 says x is, x is directly proportional, so it'll be multiplying by k, to the square of z. The square of z is z squared, and inversely proportional. Okay, so inversely proportional means I divide, and I'm inversely proportional to y. So now that I have that, I'm going to figure out which one that is, and that looks like option E. So at this point, what I would like for you to do is finish these matching ones down through 7. So go ahead and pause the video now so you can do those. So here are my answers. Number 2 is A, number 3 is G, number 4 is B, number 5 is D, number 6 is C, and number 7 is F. And if you did not get any of those correct, please pause the video now and see if you can fix the mistakes. Moving on to the YAM problem. So again, we're not going to solve this. This is a differential equation, but we're not going to solve it. We're going to do some verifying with it. But the big step that we have to take, kind of like with related rates, is take our information and turn it into the calculus. So we have a yam, and it's placed inside a 200-degree Celsius oven. The yam gets hotter at a rate proportional to the difference between its temperature and the oven's temperature. Hold on. The yam gets hotter at a rate proportional to the difference between its temperature and the oven's temperature. Okay, that's key right there. That rate is my differential equation. When the yam is 120 degrees Celsius, it's getting hotter at a rate of 2 degrees Celsius per minute. So that tells me that, let's see, I don't know my variables. In number 1, write an rate equation, a differential equation that models the temperature H. Okay, so my variable is H. So I'm going to go ahead and talk about what this 2 is. When the yam is 120 degrees, it is getting hotter at a rate. So that's the rate of change of my temperature, which is H. So dH dt is going to be 2. And that is when the temperature is 120 degrees. Now, I'm not going to need that right away. I will need that later. So number 1, it says write a differential equation that models the temperature. So that's going back to what I underlined in red. The yam gets hotter at a rate proportional to, so the rate is proportional to the difference, so I'm subtracting, between its temperature, and I'm calling the temperature of a yam a variable, and that's called H, and the oven. And the oven's temperature is a constant, it's 200 degrees Celsius. So here is our differential equation. This is our very general differential equation. Now, the H being in my differential equation is great. The K, however, is not. So that's what I need to use my information that I wrote down in red to actually find what K is. So right now I'm going to do some substituting, and I know that dH dt was 2. So I have 2 is equal to K times, and my dHdt is 2 when the temperature of the oven is 120. So 120, sorry about that, minus 200. So I hope you can see what I've substituted in, and that's just what I have written in red. So now I need to solve for K, and when I work this out, I get 2 is equal to K times negative 80, and I have 2 divided by negative 80 is equal to K, and I'm just going to write it on this side, is negative 1 over 40, and I'm just going to leave it like that. So that's how I'm going to write my differential equation, replacing the K. And this is my differential equation. dHdt is negative 1 over 40 times the quantity H minus 200. So moving on to the next one, again we're doing some verifying. So we're going to verify that this particular H right here is a solution to my differential equation that I wrote for number 1. So the first thing I need to do is actually find what dH dt is for this particular equation. Derivative of 200 is 0. I'm going to have negative 180 times negative 0.025 times e to the negative 0.025 t. So I can simplify that, and negative 180 times negative 0.25, you know, you need to check my work, I believe is 4.5 e to the negative 0.025 t. So that's what dHdt is for this particular h. And again, that's for that h that's in green. So I'm going to just plug in um, and see what I get. So I plug this in, 4.5 e to the negative 0.025 t. The question is that equal to negative 1 over 40 times h, and I have an h to plug in, 200 minus 180 e to the negative 0.025 t, subtract 200. So when I look at that, I look at my parentheses first, and I see I have a positive 200 and a negative 200, so those are going to cancel out. So I now have negative 1 over 40 times negative 180 times e to the negative 0.025t. And I believe, check my arithmetic, that negative 1 over 40 times negative 180 is again 4.5 e to the negative 0.025t. And these two things are the same. So I have verified that this particular h that is in the green box is a solution to my differential equation that I wrote in problem 1. It also said verify that the yam had a temperature of 20 degrees at time t equals 0. So I'm going to go ahead and plug in 0 for t and figure out and check to see if the temperature is 20. I'm going to kind of do that right here in the middle. So my temperature should be 20 when my t is 0. So e is going to be raised to the 0, and e to the 0 is just 1. So is 20 the same as 200 minus 180, and 200 minus 180 is 20. So that is true. I have verified that as well. So we're not going to actually find the solution to this particular differential equation algebraically, but we are going to do another one. So at this point is when you need your own piece of paper to work one differential equation with me. So the differential equation we're going to solve is this. And we have some information that we've been given about the actual equation, and y of 0 is equal to 4. So what we're going to do is we're going to solve this for y, and we are going to use the fact that y at 0 is 4 to solve for any constants that we may get. So the first thing that I need to do is I need to get my dy on the same side of the equation as my y's. Same note, I need to get my dt on the same side. You're going to do this actually at the same time. It's not really two steps. I'm going to get dt on the same side as any t's. Now, in this particular equation, we don't have any t's. So I really just only care about getting the dy's with the y's. So this first step, I'm actually going to multiply both sides by dt. So when I do that, I get dy is 3y plus 3 times dt. Now we always want to be multiplying. We don't want to distribute anything. At this point, we want to divide both sides by 3y plus 3 to make sure my dy is on the same side of the equation as my y. Now, I can't divide by my dy, I can't divide by my dt. I need those to be sort of in the top of any fractions that I would have. So I'm going to have dy divided by 3y plus 3 is equal to dt. And again, all I did was divide both sides by 3y plus 3. Now, at this point, I would try and simplify anything if you can. So simplify and well, right now we're just going to simplify. So to simplify that, I see that I have a 3 and a 3 right here. So I'm going to take a 1/3 out. And then I'm going to rewrite this as 1 over y plus 1. And then I have a dy. So from here, what I want to do is I want to take the antiderivative of both sides, because I still have this dy, I still have this dt, and that's how I can get rid of those, so to speak. So I'm going to leave the 1/3 actually on the outside of my integral symbol. It's just a constant and it doesn't need to be on the inside. I don't have to have it there. So this is what I now have. So I'm taking the antiderivative of both sides of my equation. So when I do that, my 1/3 stays. And what is the antiderivative of 1 over y plus y? Well, antiderivative of 1 over something is the natural log of the absolute value. And of course, I would have a plus c. I'm just going to talk briefly about this plus c. And then the antiderivative of basically 1 dt is going to be t. And I'm going to have some other constant right there. Differential equations you can get bogged down in pretty quickly, so I suggest that you put your plus c only on one side, because technically I could subtract my c1 from both sides of the equation and I would have a different constant with my t. And I don't care what these individual constants are. Eventually I'm going to have just one single constant, but I don't have to know what these numbers are each step of the way. So I'm going to recommend that we only add your plus c to the right side of the equation. And I'm going to say that should be the more simple side. So I'm going to rewrite that with just my plus c over on one side. And I'm going to call that a C1, even though I've already called something C1, I'll call that C3. So at this point, I need to solve for y. That's really what I need to solve for. So the first thing I'm going to do is I'm going to multiply by 3. Solve for y. So I'm going to multiply by 3, and I get natural log of y plus 1 is equal to 3t plus 3 times c1. Well, I don't care what c1 is. I just know it's a different constant now. So I'm just going to call it c2. Now that I've done this, I've got to get my y out of my natural log. So to do that, I'm going to take e to the both sides. So I'll have this. I'm going to go ahead and put parentheses around that one just so it's easier to see. And I'm going to do e to the on both sides. And when I do that, I now have e to the natural log of y plus 1 is just y plus 1. And let's talk about this. This is e to the 3t times e to the c2. That's really what I'm doing when I add those exponents. If I had had x to the 5th, that's the same as x to the 3 plus 2, which is the same as x cubed times x squared. So that's basically the idea that I've used here. Now, what I do want to talk about, though, is this thing. E raised to a constant is still just a constant. I don't care what the individual constants are, but that thing I have circled in red is a constant. So I'm going to rewrite this again, calling that a constant, putting it in front, and call it C3 times e to the 3t. And now to get y all the way by itself, I just have to subtract. And I now have C3e to the 3t minus 1. Now, I don't have to call this C3 anymore. I am finished doing anything because I've gotten my y by itself. So I could just call that C instead of C3. So we could just write it just like that. So now, this is great. I've done so much work. I've done all this stuff. This is awesome. Now I need to plug in my information that I knew. So that's your step 7. Plug in given information and solve for C. And we did that with the YAM differential equation when we had to find K. So at this point, I knew that y of 0 was equal to 4. I'm not scrolling back up to show you. But y of 0 is equal to 4, which means 4 is what y is going to be when I plug in 0 for t. So I have c e to the 3 times 0 minus 1. And that gives me 4c. And e raised to the 0 is just 1. So I really just have c times 1, which is c, minus 1. And then I can add 1 and get c is equal to 5. And so all I have to do at this point is rewrite my differential equation plugging in my c. Oh, not my differential equation. Rewrite equation for y, plugging in c. So I now know I have y is equal to 5e to the 3t minus 1. And that is your differential equation. I do apologize for the length of that video, but I really wanted you to see one differential equation before you came into class. We'll work many more when we are in class, and I hope you have a wonderful evening. I will see you soon.